Okay, so let's do an application problem involving taking the derivative of a trig function. So directions here ask us to find all x coordinates on the half closed interval from 0 to 2 pi. On the curve, y is equal to the sine of 2x minus 2 times the sine of x, where the tangent line is horizontal. Okay, so we want to find where the tangent line is horizontal. We're looking for where the slope or the derivative of the function is going to be equal to 0. So let's go ahead and take the derivative of this function. So the derivative of the sine of 2x is going to be the cosine of 2x times the derivative of the inner function. The derivative of 2x is going to be 2 minus 2 times the derivative of sine is going to be cosine. Okay, and we want to find where that derivative is equal to 0. So good news is we have both functions written in terms of cosine. The problem that we have is the arguments of the two trig functions are different, and we can't figure out where that expression is going to be 0 unless we make the arguments the same. So what we have then is we have to take the first term, the cosine of 2x, and rewrite it using our double angle formulas. Well, we have 3 double angle formulas to use. It only makes sense to use one of them, the one involving cosine only, because if we do the double angle formula involving sine and cosine, then we work a sine function in here, which is going to be problematic for us to figure out where that's going to be equal to 0. And if we use 1 minus 2 sine squared, like again, that works another trig function in, which is going to be problematic for us figuring out where that's going to be equal to 0. So we're going to replace cosine of 2x with 2 cosine squared of x minus 1. And then what I'm going to go ahead and do is I'm going to factor a 2 out from both of these expressions and then just rearrange the order of the terms. So if we factor a 2 out, that leaves us with 2 cosine squared of x minus the cosine of x minus 1. Again, I just factored those 2's out of both expressions and then reorganized or reordered the terms, the resulting terms. Okay, so this is factorable. I can factor 2 cosine squared minus cosine minus 1. That's going to factor to 2 times the cosine of x plus 1 times the cosine of x minus 1. So that product is going to be equal to 0 when either 2 cosine of x plus 1 is equal to 0 or the cosine of x minus 1 is equal to 0. So we're going to isolate the trig functions in both of these equations. So that happens where the cosine of x is negative 1/2. And then for the second equation, where the cosine of x is equal to 1. So we're only looking for the solutions on the interval from 0 to 2 pi where that occurs. So we know cosine is going to be negative 1/2. Cosine is going to be 1/2 at reference angle pi over 3. And we know that cosine is negative in quadrants 2 and 3. So the angle in quadrant 2 with reference angle pi over 3 is going to be 2 pi over 3. And in quadrant 3, that angle is going to be 4 pi over 3. And then cosine is going to be equal to 1 at the quadrantal angle of 0. So those are your 3 solutions to that equation in particular. Okay, so again, I know you guys have AP tests this week, so I'm going to try to keep these lessons here, or this lesson, as brief as possible and get right to the point. I'm not going to do as many examples. You guys can practice with the homework assignment that I give you. Okay, so last topic for us deals with derivatives of inverse trig functions. And I'm going to show you like 2 approaches that you can use to like come up with the derivative. First one, like, it's your choice whether you choose to memorize this or not. I'll show you the process that you can work through to actually like come up with and derive these derivatives. So the derivative of the inverse sine of f of x is going to be 1 over the square root of 1 minus the argument of the function f of x quantity squared. And then using chain rule, because you have a composite function there, you're going to multiply that by the derivative of the inner function, which is f prime of x. The derivative of inverse cosine looks exactly the same as the derivative of inverse sine, except that it is negative. So that's negative 1 over the square root of 1 minus the argument, f of x squared. And then using chain rule, we multiply that by the derivative of the inner function. And the derivative of the inverse tangent of f of x is going to be 1 over 1 plus the argument, f of x squared. And then using chain rule, we're going to multiply that by the derivative of the inner function. And what I want to do is we're going to take a look at like how we mathematically come up with the derivative for inverse sine and inverse tangent. The derivative for inverse cosine is going to be exactly the same as the other two derivatives that we're going to look at. Like the process is going to be exactly the same. Okay, so let's take a look at how we actually come up with these derivatives. Okay, so if we say y is equal to the inverse sine of f of x, like we don't know how to take the derivative of an inverse sine function. Okay, so just like we did when taking like the derivative of just a standard inverse function, what we're going to do is we're going to take the sine of both sides of this equation. So that's going to make the sine of y equal to, when we take the sine of the inverse sine of f of x, we're taking the composition of two inverse functions. They wind up canceling one another out, so that just leaves us with the argument f of x on the right hand side. Okay, so what we can do now is we can take the derivative implicitly. So we're going to take the derivative of both sides with respect to x. So the derivative of the left-hand side is going to become the cosine of y times y prime. The derivative of the right-hand side becomes f prime of x. And then we have y prime equal to f prime of x over the cosine of y. Now, at first glance, you may think, okay, well, I'm done taking the derivative, but that's not the case, because when we look at our original function, we have y written explicitly in terms of x. So our derivative has to be written explicitly in terms of x. Well, how are we going to do that? Well, the way we're going to do that is we're going to go to this line right here, where the sine of y is equal to f of x. And we're going to construct a right triangle based on that relationship. Okay, so when I draw a right triangle here, this is going to be our angle y. We know the sine of y is f of x. So sine is the ratio of opposite over hypotenuse, which is going to make the side opposite f of x. The hypotenuse 1. And then you can use the Pythagorean theorem to find this missing side length, which is going to wind up being 1 minus f of x quantity squared, and then you're taking the square root of that quantity. Okay, so once we have that picture drawn, now we can determine what the cosine of angle y is. The cosine of y is going to be the side adjacent over the hypotenuse, which is going to make the cosine of y the square root of 1 minus f of x quantity squared. Okay, so that's how we mathematically like come up with that derivative formula. And you can do the same thing for the inverse cosine of f of x as well. Now, it's your choice. Like, I'll show you with one of the examples we work, whether you choose to memorize the formula or actually like work through a derivative using the same process that we did to derive the formula. I like memorizing it because it makes the problems go a little bit faster, but I think this is a really cool, interesting way to come up with the derivative of these inverse trig functions based on like what you know about right triangles. Okay, let's do the similar process for y is equal to the inverse tangent of f of x. Okay, so if we want to like actually derive this derivative, we're going to take the tangent of both sides. So we get the tangent of y equal to f of x. Then we're going to use implicit differentiation to take the derivative of both sides. So the derivative of the left-hand side becomes the secant squared of y times y prime. The derivative of the right-hand side is f prime of x, which makes y prime equal to f prime of x over the secant squared of y. And we run into the same problem that we did with the previous part, okay, where we differentiated inverse sine. Our original function here is written explicitly in terms of x. We want the derivative written explicitly in terms of x as well. So we need to come up with an expression for the secant squared of y. To do that, we're going to use the tangent of y is equal to f of x. We're going to use that expression to diagram a right triangle here. Okay, so there's our angle y. If tangent is f of x, that's going to make the side opposite f of x, the side adjacent 1, and that's going to make the hypotenuse the square root of 1 plus f of x squared using the Pythagorean theorem. Okay, so that makes y prime then equal to f prime of x over the secant squared of y. Secant is going to be hypotenuse over adjacent, which is going to be rad 1 plus f of x squared. But we're not finding the secant of y, we're finding secant squared of y. So the square and the radical cancel one another out. That leaves us with 1 plus f of x quantity squared. Okay, and that's how we come up with the derivatives of those inverse trig functions. Okay, so let's just do 2 quick examples with this, and then that'll wrap up this lesson, and I'll post the homework assignments on Schoology for you guys to work on. So I'm going to work out number 1 both ways. So just utilizing, memorizing the derivative definition, and then we'll also work it through in the process that we use to actually derive the derivatives. And in the second example, I'm just going to memorize the derivative for that. Okay, so if we memorize the derivative y prime here, that's going to be equal to the derivative of inverse tangent, which is going to be 1 over 1 plus the argument 4x quantity squared, and then we multiply that by the derivative of the inner function, which is 4. So that's going to make y prime equal to 4 over 1 plus, if we square 4x, that's going to become 16x squared. Okay, the other way to do this is we're going to use a similar process that we use to actually come up with a derivative. So we're going to take the tangent of both sides. We get the tangent of y equal to 4x. So we're going to apply tangent to both sides. And then we can go ahead and differentiate this using implicit differentiation. So the derivative of tangent is the secant squared of y times y prime. The derivative of the right-hand side is 4. When we isolate y prime, that's 4 over the secant squared of y. And then our original function is written explicitly in terms of x, so we want to write the derivative explicitly in terms of x as well. So we're going to take this statement right here, where the tangent of y is equal to 4x. We're going to draw ourselves a right triangle that satisfies that trig equation. So there's our angle y. Tangent is 4x, so that makes the side opposite 4x, the side adjacent 1. The hypotenuse using the Pythagorean theorem is going to be the square root of 1 plus 4x quantity squared. So the secant of y will be hypotenuse over adjacent, which is rad 1 plus 4x quantity squared. But we want to find secant squared of y, which is going to be 1 plus 4x squared, which whenever I simplify y prime, that's going to be 4 over 1 plus 16x squared. So again, I don't care what approach you use. whatever one you think is easier. I think it's probably easiest to, like, it makes the calculus easier, and the algebra easier, and like the amount of work you have to show easier if you memorize the definitions. But if you're not keen on memorizing stuff and you want to work things through intuitively, that's okay as well. Okay, I'm going to work the second one through just utilizing the formula for the derivative. So y prime here is going to be 1 over the square root of 1 minus the argument, which is rad x, quantity squared. And then using chain rule, we have to multiply that by the derivative of the inner function, which is 1 over 2 rad x. So that's going to make y prime, when we simplify, 1 over 2 rad x times rad 1 minus x. And then, like, you can leave things in that form, or on bottom you have the option as well of, because you're multiplying two radicals, you can take that product and combine it under a single radical. So if I distribute x across both those terms, we get rad x minus x squared. That's probably the most simplified version for that derivative. Okay, so that wraps up this lesson, and we're officially done learning for the year. Congratulations.